For the past week, we have been in Chapter 8, Section 2, discussing how to classify critical points as either local maximums or local minimums, or neither, using the first and the second derivative test. What I want to go back to is something that we covered in Chapter 3, which was finding absolute maximums and minimums. And there is a theorem that we're going to talk about. It's called the extreme value theorem. And when this video is over, you guys are going to work on some group work that is going to incorporate what you learned in Chapter 3 with finding absolute maximums and minimums, and then also incorporating what we've done over the past week with finding local minimums and maximums. The extreme value theorem states that if you have a continuous function on a closed interval, that there has to be an absolute maximum and an absolute minimum. And the key words to focus on is that your function has to be continuous, and it also has to be on a closed interval. So notice that my interval is from A to B, and then it has brackets. That means it includes the x value at A and the x value at B. So continuous and closed interval, if that is the case, then your function has to have an absolute maximum and an absolute minimum value. And that means that at the absolute maximum, that's the largest y value on the entire domain of f, and you have an absolute minimum at the smallest y value on that domain of f. And so according to this, here's just a little graph to illustrate how you can have an absolute max and absolute min, and then also have local extrema is what we call them. So we have an absolute minimum at the very first x value at x equals a, because this is the smallest y value on the entire domain. At x equals d, we have an absolute maximum because that is the largest y value on the entire domain of f. And then we have a couple local minimums. We have one at e, and we have one at the endpoint b, and then we have a local maximum at x equals c. A local, remember, is just that relative to the points around it, it has a larger y value, and that's why we specify a local or a relative versus an absolute. Absolute means it is absolutely the largest y value or the smallest y value on that domain. Absolutes don't have to happen on the endpoint. So for example, we started at x equals a, and that happened to be the smallest y value, but this could have been reflected, and you could have had an absolute maximum at the endpoint. You could also have an absolute maximum or minimum somewhere in the middle, and so it doesn't have to be at an endpoint. So like at x equals d, we have an absolute maximum. And so we're going to go through the steps that we went through back in Chapter 3 on how do you determine an absolute maximum or an absolute minimum. And so we call that the closed interval method. And so it says to find the absolute max or min values of a continuous function on a closed interval, the first thing you do is find the critical points of f in the interval a to b. And so notice that this interval a to b is that you can't have a derivative at an endpoint, and so that's why I changed this to parentheses. So what we have to do in this step 1 is find f prime. You have to find the derivative and then set it equal to 0. Once you have found those critical points, you plug the critical points back into the original function, because we're trying to see which one has the largest y and which one has the smallest y value. And then not only do you have to plug the critical points, you also have to plug the endpoints in to determine which one is the largest and the smallest. So you'll find all the y values at the endpoints and at the critical points, and then just from those values, that's where you determine the largest y value is the absolute maximum, the smallest y value is the absolute minimum, and the ones in between could be the local maxes and mins, and then that's where you will be using the first or second derivative test to determine local maxes and local minimums. So our first example is f of x equals x minus 1 to the fifth power plus 4 for x existing in the interval from -1 to 3. And so the very first step that we have to do is that we have to find our f prime. And so just using power rule, we bring the 5 down. 5 times x minus 1 to the 4th. The derivative of the inside is 1, so I didn't write that. So then we set this equal to 0, and then we solve for x. And one thing to make note that this is a 5th degree polynomial, so we know that it is a continuous function on the interval from -1 to 3. So then set the first derivative equal to 0, and when you solve, you get x equals 1. So then what we're going to do is plug 1 into the original function f. We're also going to plug in -1 and +3, since those are the endpoints. And when you do that, you get f of 1 to be 4. You get f of negative 1 to be negative 28, and you get f of 3 to be 36. And so that is telling us the one that has the smallest y value, which is negative 1, is the absolute minimum. And the other endpoint, 3, is the absolute maximum. So f of 1 equals 4 is a critical point because that's when the first derivative is 0. And then from here, this is where you would have to either use the first derivative test, so what is going on before 1 and what's going on after 1 with the first derivative to determine if it's a local max or a local min, or you could find the second derivative and plug 1 into the second derivative to determine if the function at this point is concave up or concave down. And then from there you can classify it as a local maximum or a minimum. I'm not going to do this in the video, but I'd like you to do that on the group work. The second example that we have is a third degree polynomial. So I know that that is a continuous function. And so then our interval is from 0 to 6. So the very first step in finding an absolute max and min is to find the derivative and then set it equal to 0. So you get 6x squared minus 30x plus 24. You can factor a 6 out to get the 6x squared minus 5x plus 4. And then use your diamond problem. What two numbers multiply to 4 and add to a negative 5? It would be negative 1 and negative 4. And then just using zero product property tells me that my critical points are at 1 and 4. So then I'm going to plug 1 into my original function, my cubic, and then also the 4. And then I'm also going to plug in 0 and 6. So f of 1 is 18. F of 4 is negative 9. And then don't forget to plug in your endpoints 0 and 6. So 0 is 7, and I get a y value of 43 for 6. And therefore my smallest value, my absolute minimum, is at an x value of 4 and a y value of negative 9. And then my largest y value occurs when my x value is 6, and so my absolute max is at 643. And so this just shows that you can't generalize that your absolute maxes and mins are going to occur at the endpoints or the critical points. And so one of them, the absolute min, occurs at the critical point, and the absolute max happens to occur at an endpoint. Another thing to make note is that let's say you set the second derivative equal to 0 and you get a third value, or you get a value that isn't in the interval, then you don't need to plug it into the function. If it's not in the interval, then it's not considered a point to have a maximum or a minimum. So make sure that when you find your critical points that they exist in the interval. And then the last example that I have is f of x equals sine of x and cosine of x for your domain to be between 0 and pi. One thing to know is that this is a sinusoidal function that exists with sine and cosine, and so I know that the domain or that the function is continuous across all the domain of x's, and so I know it's a continuous function on the interval from 0 to pi. So then I'm going to find the first derivative. And you don't forget that you have to use product rule, 2d1 plus 1d2, and this simplifies to cosine squared of x minus sine squared of x. Set it equal to 0, and when you bring the sign over to the one side, so this is saying sine squared equals cosine squared, so where in the unit circle do sine and cosine, where are they equal? And when you square them, you get the same value. That would be between 0 and pi, and you get your x values to be pi over 4 and 3 pi over 4. And so even though sine and cosine are same but opposite at 3 pi over 4, when you square them, you get the same value. So those are my two values. I'm going to plug those into the original function. I get 1/2 and negative 1/2. And then don't forget to plug in 0 and pi. So both 0 and pi give you a y value of 0. And so then your absolute maximum is at pi over 4 1/2, and your absolute minimum is at 3 pi over 4 and negative 1/2. So for the remainder of the hour, you guys are going to be working on some group work. The first 6 problems, 5 through 10, is just you're given a graph and you need to determine if there is an absolute maximum and absolute minimum according to the extreme value theorem. And then for numbers 11 to 18, the directions say to find the extreme values, so that's those steps that we just walked through for examples 1, 2, and 3. But I also want you to find the local maximums and minimums using the first or the second derivative tests to justify your answers. So make sure you add that into the directions. So that is it. Have a good day and come in with questions on the extreme value theorem tomorrow. If you finish the group work, you can hand it into the box. If you do not finish the group work in class, you need to finish it for homework. Have a good night.